Thank you. I'm going to speak in Japanese. So this is the agenda for today, and I will start with the introduction, explaining the intent of the panel. So Keio Quantum Computing Center. Here we have this collaboration of the last 6 years or so. And 9 companies are participating. IBM's premium machine is available in this environment. And killer application for quantum computing. We have been doing joint research, including multiple national projects. And strong support and collaboration with IBM has been enjoyed. It means a great deal that we have access to this powerful environment. And today we have 4 companies represented. We have a very close collaboration. Quantum algorithm development, this is all about expertise and know-how. Rather than companies working alone, separately, insights gained should be shared among multiple companies. This is something that we feel very strongly about. For example, just yesterday, Jesa and Mizuho, I know that they're completely different industries, but we had a very close discussion with them yesterday. It's very important to be able to have this kind of environment, and we're very active in R&D. People participate from different backgrounds, chemistry, industry, and also material science. And we need people from different backgrounds. Otherwise, if the scope is too narrow, quantum computing can prove challenging. We need an approach to find opportunities in various fields and areas. And industry and academic, important problems are the focus of our R&D. And I would like as panelists to introduce themselves. Hello, I'm from Mitsubishi Chemical. My name is Kochi. In 2007, I joined Mitsubishi Chemical Group. Simulation and material informatics has been my area of expertise, and in 2018, Keio University started the Research Center for Quantum Computing, and our company started participating. Now, I'm resident in Keio University for the research. So over the last 6 or 7 years, I've been researching quantum computing. Next slide, please. On this slide, you can see the overview of the activities at Mitsubishi Chemical with regard to quantum computing. So we collaborate with academia, industry, and consortium national projects. As far as academia is concerned, we have Keio University, the University of Tokyo, University of Toronto, and AIST. Mostly development of algorithm and verification of use cases. As for the industry, we do mostly joint research with vendors who have the machine. For example, IBM and Xanadu, Canada, PsiQuantum, and also Fujitsu in Japan. Algorithm developed in academia. How can we scale this and commercialize this? That's the focus in the industry collaboration. And then we participate in national projects as well, so that there is a private and public joint effort. For example, SIP project. This was a university-led project. We participated starting from last year, for example. Next slide, please. So over the last year, these are some of the things that we have researched. Top left is a tensor combined with a Monte Carlo. So this is a quantum algorithm that we have developed. NISQ's computing resources, we can go beyond that size, and we can do large-scale quantum chemical calculations. A paper was published with this theme. Top right, this is a QPE. Advantageous algorithm. This only works on FTQC, but in this research project, we try to reduce the computing resources, and with an IBM machine, 33-qubit QPE calculation is now possible, which is at the highest level, and we have just submitted the paper for this. Bottom left is classical AI and also optimization calculation in order to identify new materials. I will have a presentation later on, so if you're interested, please join us for my presentation later. Last but not least, AI and quantum computing integrated into this mathematical methodology. Toronto University and NVIDIA working to combine the quantum computing and the AI, and we actually tested this in the actual machine to prove that this algorithm, this methodology works. And we plan to submit paper for this. And this is something that we did together with the Kyoto University. We really appreciate their support. That's all from me. Thank you. Thank you very much. I'm from JSR. My name is Sakuma. Material science and the semiconductor simulation has always been my focus. I joined JSR in 2021. And currently, I'm a joint researcher at KQCC. Perhaps not many people in the audience know about JSR, but we are a chemical manufacturer in Japan, mostly working in the area of a manufacturing process of semiconductor manufacturing and also display manufacturing. We manufacture the materials for that. We also have life science business, providing materials for pharmaceutical products and also synthetic resin. So these are the main revenue sources for our company. We are basically material manufacturer, so high quality material, new quality. We really need to continue to develop these to make the business work. And the reason that we invest into quantum computing is because if we use quantum chemistry, we can do high precision simulation, and also we can use machine learning to predict the materials. This is very interesting. And we have been part of KQCC from the time of the foundation as a company member, industry member. At the bottom of the slide, you can see some of the examples of my recent work. On the far left, what you see is a phase estimation algorithm. For example, light absorption spectrum for a water molecule can be calculated high precision. In the middle, this is Mitsubishi Chemical Kanno-san's main work, and the co-author actually includes Koji-san from Mitsubishi Chemical and also Yamuachi-san from SoftBank. So this is a joint research and a joint paper. So 33 qubit, this big resource of IBM is used to calculate at high precision. This was a big result, big outcome. On the right-hand side, we can see the quantum machine learning example. So light cone or kernel method is used to identify the important parts of quantum circuits. feature selection is a potential application for this. That's all from me, and thank you for this opportunity. Well, I'm sorry that the clock was not working, so I'm having difficulty doing the time management. So on my clock, I have 39 minutes left. Is this correct? Is it okay to continue? Please go ahead. Yes, my name is Sato, Toyota Central R&D Labs. So computational dynamics has been my focus, which is part of machine engineering. And then after obtaining doctorate, I joined Toyota in 2019 and then started research on quantum computing. And from 2022, I've been working as a collaborator at this center. Now, in the computational dynamics, we use partial differential equations, and using that, I'm trying to accelerate the quantum computing. That's my focus.
Within this Toyota Center, we have been working on the quantum research. So I'd like to speak about what we have been working on in this quantum team. Our goal is to have the innovation for the manufacturing, and we try to solve the problems of the society. And so we have been trying to work on the enhancement of the quantum computing and computer technology. And one of the applications would be to use it for mobility services and social system well-being. And also we are thinking about using this for such areas as energy and manufacturing. So we try to work on the optimization and the quantum devices and sensors and material designing and CAE. Through this activity, we try to lead the activities of Toyota Group. And that's a kind of the quantum computing foundation that we are aiming to create. And so we ourselves alone might not be able to realize these goals. That's the reason why we try to have the external collaboration. We have Toyota Group companies and also the Denso Aisin and the Toyota. We have been participating in the industry academic collaboration and communities, and the collaboration that we are having right now with the Keio is one of the most important. And then this is the collaboration with the KOCC, and I'm showing you here what we have been able to achieve on the left-hand side. So the first is the wave, the VBD. So this is the applied H's for hyperbolic PDEs. So we came up with the quantum algorithms for that. And we have been doing this with on the Oracle base. So we have the hypothesis, this has been built on the logic. But now this is based on the actual implementation. In the center is something we have worked with Sony. And then also on the right-hand side is another the activity of QCC. So this is a very simple. We have been working on something very simple, but as in the case in the center, for example, if there is a obstacle or something, the foreign, then as can be seen, you see the reflection of the wave, then they expanded its structure, and then this is the general purpose simulation, for example, thermal simulation. This has been the expanded version for that, and then the right hand side is slightly different, but the examples here are the optimization of the combination, and this is QLAC, and so we try to combine the QLAC. So this is what the unified quantum optimization, recursive QA/OA, and the QRAC. So, thank you very much for inviting me here. Thank you. My name is Yamamoto. I'm from SoftBank. After graduating from the university, I got into this field, and I joined SoftBank in 2006. And in the last 20 years, I have been with the SoftBank, and this is my second year working with KPCC. And then 3 years ago within SoftBank, we established the division for the quantum technology. So we have to say that as SoftBank, we have been doing this in the last 3 years, which is limited, but we have been very much active in this field. I have been with the cable system for the optical cable systems, and so the the optical pulse transmission simulation and others. And so I sometimes visited the actual working site. And within the SoftBank, I have been solely working on the development of the operational systems and for example, recovery, automation of the service. And also I have been working on the implementation of the automation systems. And then we have been also introducing AI and also the enhanced the learning based discovery. All these have been done with the classical computing, but what we try to do is to introduce the quantum computing. So for the major systems, we utilizing the data set of the major systems, using the quantum kernel within the IBM Kawasaki. We have had the 30 qubit, the failure diagnosis systems has been done. And we have been working on we were able to conduct the experiment for the diagnosis of the failure. This has been announced in the Quantum Week last year. Moving on to the next. This is what we do within the SoftBank. So we try to visualize the future network. So all the central data and mobile customer data and the enterprise data, all these should be put onto this. So all the amount of data would be very large, and they would become very much complicated. They would come into the company. So we have the distributed computing for the network itself, and also we have these computers and supercomputers on the back end, and also this could be connected and interconnected with the quantum computings. So we have been thinking about the scale up of the computation functions. And so for the AI LAN, we'll have the virtual mobile network. So this could be implemented onto the AI function, and the infrastructure are being built so globally. So we try to have good alliance with that. And this is for the traditional network. And then in what way are we able to tackle with the quantum technologies? Again, this is about the machine learning for quantum technology. So the direction is that the machine learning for quantum, and then we have the static, the image, and also the letters. And so we could have the references, inferences, and also we could have the time-dependent dynamic data. And also we have the network, and in what way are we able to have the scale up or the scaling of that. And also for the security, for the quantum networking, I think for with the combination of the security technologies, in what way are we able to create an infrastructure? These are the things that we try to do. And now we have NATO challenge, so-called. And I have been involved with the submission of the themes, and now I'm working on the solution of the problems. So there have been two issues submitted, and one is the network, the promotion, and then the two on the right-hand side is the preparedness for the disasters. We have to work on the scaling of the quantum computing in the network. And so this is the FedEx running. So this is the configured learning systems for the quantum, and this is what we try to do. In the center is the detecting humans trapped under rubble. So these do save and rescue humans under the rubble. So that should be done within 72 hours. So this is the problem raised. So there could be many things in the field of research and utilizing the dataset. And then in what way are we able to utilize algorithms, and end-to-end scenarios should be drawn. And there are many more things that we have to do. And then on the right-hand side, this is the glacial lake outburst of flood. For example, we sometimes use the glove, and then on the Himalayan, the mine area, because of the global warming, this could be destroyed almost instantaneously. This is a issue related to global warming, so they are very much related to human lives. So these are the challenges we try to take on. That's all. Thank you. Thank you very much, all of you. From now, I'd like to follow the agenda items shown here. So let's take a look at what we have to do on the day-to-day research. So have the team from different the industries, and then it is important to think about the collaboration across different industry. So I'd like to go back here. Sakuma-san and Koji-san, these two individuals introduced the algorithm, the TCC. So I'm also involved. This is for the computational energy calculation, the Mitsubishi Chemical, JCL, and IBM, and also SoftBank. And so this is the collaboration among different companies, rather. So I'd like to go back to this. Could you tell us a bit about why you decided to tackle on this?
やっぱり
It's really appealing that there is an advantage. QP methodology can be utilized, and you can do the calculation using a real machine. And with regard to quantum computing, quantum calculation, we can generate something that can be called a game changer. So this algorithm is really a game changer. But this only runs on FTQC. Difficult to do this calculation based on the current quantum computers. But in the near future, QPE, we want to see this operational. And this is why we started focus on this research. So FTQC, you have expectation that this will definitely work in the future. Well, we want to achieve this in the nearer future than FTQC. Well, tensor network, Bayes, and also phase estimation, and Q controls method. So you employed every possible methodology to make it work. That was very impressive, actually, from my perspective. Sakuma-san, how did you enjoy this? What's interesting about this? Well, wave function in quantum circuit, this is actually very difficult because we are looking at the base state and also excited state, higher level energy state. We are trying to capture both at the same time, which is very challenging. Kano-san from Mitsubishi Chemical showed that tensor network can be used for higher efficiency, and this is the most important aspect of this project from my perspective. And the time development is also a very difficult topic, even if you use quantum computing, but tensor network can be utilized there as well. And I've been engaged in many discussions, and I've learned a lot. Tensor network is a classical but really powerful methodology, so you're trying to use everything you can. But for actual implementation, circuit may be too long. Q control software is used. So can you please talk about how this was decided? Q control helped me with a kernel experiment, and I saw that it was really powerful. So participating in KQCC and then seeing real result, I think the timing was right. It was a very good experience for me. So the circuit length is now 1/10 of what it used to be. So I think this was really powerful. Maybe they're in the audience as well. Sato-san, I want to talk about your research now as well, especially PD simulation, shown in this slide. Maybe we can find a list of authors somewhere. Yes, maybe no list of authors, but IBM myself, I am also involved on Sony. So what kind of collaboration was this? Example on the left, this is something we did together with IBM. I have already explained this very briefly, but the simulation was basically Oracle-based, and there is precision guarantee, but how to implement was a challenge, and IBM's researcher and us discussed a lot about this and found a way to effectively implement this. That's that left example. And at that time, this was a very simple question that we dealt with. But after that, Tezuka-san from Sony discussed something at KQCC, and in order to explain or express geometry for Hamiltonian simulation, there is a logical compression method to explain the semiconductor circuit, and he suggested that we use this, and we did. So even if there is some kind of complicated shape or geometry involved, it can be now expressed using quantum computing. Logical compression, were you already familiar with that? Was Tezuka-san already familiar with that? I don't know the background, but he knew that it was used quite commonly in semiconductor design. Now, this is still ongoing, and long circuit was again a challenge, and using AI was one way, but you try to reduce the circuit using manpower, and IBM was helping you a lot with that, I think. So I think it was a great collaboration. Using AI to reduce the circuit is one approach, but there's also a lot of a manual approach. Sometimes people can find potential reduction. Itoko-san actually is maybe better than AI, so we call him Itoko compiler. So long experience does provide a lot of benefit. Now let's move on to the next topic, if that's okay. FTQC. Early FTQC, we see many great algorithms appear every year. We definitely want to take advantage of those. So let's talk about expectations. Sakuma-san, you are actively using FTQC algorithms. What is your view? Water molecule light absorption spec algorithm. This was based on phase estimation. And if you try to do this with classical computing, you can do it for small molecules, but if the molecule is too large, the computation volume increases exponentially. But if you use quantum computing, the calculation is exponentially accelerated. So this is a very interesting methodology. Looking at this circuit, you can tell that the qubit, there are a lot of assisting qubits, but you can reduce the number of this using more recent algorithm. And early FTQC targeted algorithm is developed every day. It's very promising. People used to say that FTQC can be achieved maybe far in the future, but the algorithm is being developed, which can be used maybe only several years down the line for FTQC. It's very promising, and we're getting very close to developing actual materials. For signal processing, expertise were built, and that is now being applied to this area. And I'm sometimes moved to see new algorithms, filter, signal processing. All of these words are used very commonly these days. Sato-san, you're from mechanical engineering originally, so would you like to use these algorithms as well? Well, I'm not an expert on classical signal processing, but in classical computing, I know that these are the thoughts that are used quite commonly, and I understand this is also used in quantum computing as well, algorithms developing. And basically, Hamiltonian simulation is what you're aiming for, embedding a different type of simulation into another one, and you are also targeting early FTQC. Well, if you use a calculus in itself, FTQC may be a requirement, but if you just focus on specific problem and employ technique focusing on that problem and shorten the circuit, in that case, we can bring it to a scale that can be run on the actual machines that are available now. So we started with FTQC algorithm. We used Hamiltonian simulation, which has the precision guarantee. And at a small scale, we can actually run this on the actual machine. We're beginning to get there. CAE, maybe I should call it CAE. I think this has a broad potential application, so I have high expectations for this. Moving on to AI, since this was also brought up during the conversation. Using AI to assist quantum. AI for quantum or quantum for AI, I think it can work either way. So how can you use AI to assist quantum, first of all? Koji-san. Yes, this is an area of strong interest for us right now. Using AI, doing error correction to implement quantum computing. Using AI, quantum circuit can be compressed and longer circuit calculation will become possible. And GQE is the methodology that we are focusing on right now. Yes, I mentioned this during my presentation, bottom right. And this is Toronto University and NVIDIA as methodology. SSI and quantum computing, generative AI and quantum computing are combined to do the quantum calculation.
One of the major characteristics for this is that, generally speaking, we use the language model and to come up with GPT. But this is by mimicking this, we are able to come up with a special GPT to create the quantum circuit. So we have the certain sentence, and then we have the GPT, the automatic generation of GPT, and then if you use the quantum computing on a single basis, and then utilizing AI, we are able to identify the quantum circuit, which is generally speaking very difficult to identify. And also material informatics is also combined. For example, we have this kind of the molecular simulation, and then there could be many different applications, so that we can have the generative AI and the quantum computing integration could be a major use case. So we're able to see a huge potential here. Thank you very much. The Gen AI and it can create the circuitry algorithms. So this is very much in line with what we are trying to do. But again, the huge amount of data set is important. So in what way are we able to have the training data? So this is the bottleneck at this moment. So when the paper was issued, so one thing that many people said that in the case of the quantum computing, it might be difficult to generate data. And then Keio University alongside with IBM have been working on this on the actual machine on the IBM, and then error correction and error mitigation could be incorporated. And then with the IBM machine that they have at this moment, it is possible to generate data to a certain extent. We were able to confirm that. So using the quantum computing, it is possible to generate this necessary data. And to be more ambitious, for example, for the GPU simulators, we could create a large amount of data, and then with the created GPT, and also on top of that, we put that into the quantum computing, and then for the smaller ones, trained by the GPU, and then larger ones could be connected with the computers, and then this way we are able to generate data. This is something we have to consider from now onward. So on the web, there could be the huge amount of logs that shows the potential for the calculation of the algorithms of the qubit. So this is something the entire world should tackle. And for the quantum, for AI, this might be difficult. Well, I'm working on it, and the paper had not been issued, so I'm not sure whether I can disclose. But for the analyst, we try to identify the amount of features, so the dynamics can be put onto the topology, and then we can have the solution using the quantum technology, and there could be coherence, and there are many things that we want to realize. But in the case of algorithms, this is based on the situations. So again, spareability is again being discussed in terms of algorithm, and the Kami-san, the experiment had already identified this. So this is very fast. So if it is possible, so we'd like to work on the data analysis based on this. So at this point in the internet world, federated learning is already implemented. There are many papers, and what is the level of scalability and also knitting of the quantum circuit. There are many papers, but what we try to do is using the tensor network for the reservoirs, and this is the classical example of the implementation. So what we try to do is to utilize this. In that situation, maybe we'll be able to do that for the network. For the quantum AI, we have been working on the reservoir computing, and with the 120 the kilobit. So therefore, the quantum, the superior, the quantum advantage, it is very important. So we try to tackle with this. So we just talk about many things. And from now, we'd like to ask each individual to work on the summary of their project. But again, I think it makes sense to take questions at this moment. If you have any questions, please raise your hand. Thank you. These four individuals talked about various applications in various fields. Thank you so much. And then the one thing, what do you think is the kind of application that is very much close to the creation of the value in terms of business? Which one is the closest? I'm the one to answer? Well, in terms of width, the chemistry and CAE is quite large, and maybe the FTQC, whether to what extent it is close to the something that is not done by the FTQC, or something that can be done by the classical computing. In the case of chemistry, the 300, the logical qubit, so is the kind of the area realm where we are able to have a large amount of applications, because it is very high performance. So this is very much dependent on the future, the performance, and also whether it is possible to have error correction or error mitigation utilizing AI technologies. All these should be utilized properly, and then in 2030, our goal is to have the business phase introduction of the quantum computing in the year 2030. That's our expectation. And so you talked about 300 logical qubit. What about CAE? In the case of CAE, we have this supercomputer-driven large problems. In that situation, 50 to 60 logical qubit. So if we have 50 to 60, then we are able to deal with large-scale problems. And also, the basic application is linear, which is quite simple. But if we are able to have non-linear, then in that situation, it is possible for us to deal with something that is, for example, liquid. And so we have even if you have the assessment conditions, it is okay to have 50 to 60. Yes, for the qubit number of qubit, if it is 50 to 60, it's okay. But it depends on the depths. But in terms of number of qubits, it's okay. Then in that situation, for the small areas, it might be possible to utilize this. And also in the case of CAE, the number of qubit is the one thing, but also we have to deal with the depth. And also in what way are we able to deal with the state after the computation? So this is the input-output problem. This is traditionally the problem in this. So this is on top of the number of qubit. So that goes beyond the number of qubit. We still have 1 more minute, slightly over 1 minute. Thank you. Earlier, you talked about the early FTTC, and you talked about the good projection that you are able to see utilizing various technique. And this way, you were able to enhance the accuracy and precision. The Q control and the Kedma-san, and the errors you have been working on the error suppression and error mitigation. There could be many tools to enable that, but looking into that, it could be the combination of various techniques. So Yamauchi sensei talked about the circuit, the length, and it is almost the 1 to the 10th, and which is much shorter and which is very good. But on top of that, maybe shortening the circuit is one thing, but maybe there could be some other technique that is very effective. Are there any knowledge that you have about the quantum, the singular value transformation? With this, we were able to start seeing the logic for the reduction of the circuit size, and then we have the QT, and intrinsically utilizing AI, we are able to utilize a black box, and this way we are able to have the various logic, the thesis that would be conducive to the reduction of the circuit size. Why is it possible to do this? Well, about myself, I'm not able to understand this. So I think globally, many people are working on why it is possible. Why is it that the quantum algorithm is fast? So this is a fundamental question that we have to raise. And then that would lead to the new breakthrough, which should be conducive to a new discovery. That would be great. Thank you. With this, it is time to end this session. Thank you very much. Thank you.